Hello, ladies and gentlemen. I am Dr. Claudia Albers, Planet X research and professional physicist. And today I'd like to bring to you another one of my articles. This one is entitled The Planet X Effect, Heating and Ionization in Contact Regions. Now, the Planet X effect refers to the heating and ionization which occurs whenever stellar core matter makes contact with solar system matter. Now, in Article 336 entitled Stellar Nebula Cloud Structure, as in many previous articles, I mentioned that celestial bodies, i.e. planets and stars, operate like superatoms. In Article 336, I also wrote about celestial objects' electron clouds, where the electrons in those clouds have a specific energy which increases with distance from the object, and are thus like energy levels of an atom. So it is important to understand how energy absorption and emission works in atoms in order to understand how it works with star systems or celestial objects. And we have here a representation of an atom. We have a nucleus with protons and neutrons, and we have electrons in energy levels. And here we have an electron which has moved down to a lower energy level, and at the same time it emitted a photon. And the opposite here, we have an electron moving to a higher energy level. In order to do that, it has to absorb a photon. And this is also because the energy of the energy levels increases as we move away from the nucleus, so in this direction. So in order for an electron to gain energy to move to a higher energy level, it has to absorb energy in the form of a photon. Now we know that when an atom absorbs energy in the form of a photon, it often leads to an electron leaving the atom, i.e. the atom becomes ionized. And we know that an atom emits a photon, i.e. it releases energy when an electron moves to a lower energy level. So that's what's occurring here. But what would induce an electron to move to a lower energy level in the first place? I, like Einstein, do not believe that God plays dice with the universe. In other words, this does not happen by chance. There must be a reason why the electron is induced to move to a lower energy level. Now, as I explained in Article 260 entitled Planet X in the Solar System, the principle of equal energy sharing, particles interact through their gravitational fields and equally share their energy when they come close enough to each other. This means that a particle absorbs or emits energy as a result of the other particles in its environment. Thus, an electron moves to a lower energy level in an atom when the atom encounters another atom which has less energy than it does. And conversely, an atom which encounters other atoms with more energy than it has will absorb photons emitted by the atoms with more energy. This causes an electron in the atom absorbing the photon to move to a higher energy level. Thus, energy absorption or emission is dependent on the environment. An object with more energy than its environment will automatically emit energy in the form of photons or light. However, atoms emit specific wavelengths of energy which are different for different types of atoms, as these are dependent on the position of each atom's energy levels. Thus, oxygen atoms emit photons of different wavelengths from carbon atoms, for example. So if two carbon atoms share energy, this energy will be absorbed as gravitational energy. But if a carbon atom and an oxygen atom share energy, then the energy is not at the right wavelength to be absorbed as gravitational energy, and thus will be absorbed as heat instead. But in the case of an outer electron absorbing a photon, any photon energy may result in the electron leaving the atom, which then becomes ionized. And you may look at Article 337 entitled Heat and Gravitational Photon Energy for more details. And this process is illustrated here, and where the blue circles represent atoms that are the same type, and the red circles represent other type of atoms. So it could, for example, be oxygen atoms or blue and carbon atoms or red. And now what we have here is an atom that has approached another atom, and the yellow represents gravitational energy. So this atom has a lot of gravitational energy, and then this one has very little, actually none. And this means that when they approach each other, that energy will tend to leave the atom that has a lot of energy, and so that atom will emit a photon. And this will lead to this atom absorbing that photon. Because they are exactly the same type of atom, they will absorb the same, they will absorb it both as gravitational energy. So gravitational energy is emitted and gravitational energy is absorbed. And through the principle of equal energy sharing, they both end up with the same amount of gravitational energy. But then these two atoms, which are not the same as those, detect that there's an atom close to them that has lower energy than they do. Notice the energy difference is not as great, but there's still an energy difference, and that means that these two atoms will now emit photons as well. But these are different atoms, so their energy is not absorbed as gravitational energy by the blue atoms. It's absorbed as heat energy. And that means that the blue atoms now start vibrating faster. And there may be ionization as well. They may lose electrons. Electrons may leave these atoms. So there may be heating and ionization occurring as a result of this transfer of energy. But in addition, in the case of a celestial object, i.e. a star or planet, the loss of energy also triggers the flow of energy from the object's core outwards to the outer layers. And this also occurs as a result of the principle of equal energy sharing. Particles lower down inside the object lose energy to other particles closer to the surface, resulting in the energy transfer to spread through the whole object, and it eventually reaches the core. Now, the greatest heating, as we can see here, tends to occur at the contact surface. So where there is contact between particles that have high energy and particles that have low energy. And this is where the most transfer occurs, because there is the greatest change from one to the other. So you can see this one is very high, this one's very low. So this is where the most transfer of energy will occur. But as we percolate down towards the core, the transfer is not as much. As you can see now, it's from about half to full. So it won't lead to as much energy being absorbed at the second level. So it eventually reaches the core, and when the particles in the core start to lose gravitational energy, this triggers an increase in energy generation by the core, which then flows outwards toward the outer layers. And you may look at Article 240 entitled Planet X System Effect on Radioactive Decay Rate and Heating of Planets. This causes energy to be emitted from all levels of the object all the way to the surface, and causes heating and increased ionization. But of course, the layer that will experience the most heating and ionization is the layer which has come into contact with the lower energy particles. This is most likely to be the top layer, unless the stellar core matter penetrates into the planet's atmosphere. And this is illustrated again here, how this energy transfer will be greatest at the contact between the two, if this is stellar core matter. And this is also illustrated here. If we have a stellar core in making contact or close to the Earth, then energy will flow from the Earth towards the stellar core. And this means that this layer will first lose energy, but energy will flow from inside the Earth, and eventually it will flow outwards from the core. Thus, all layers of the Earth will heat up, but the layer that is most likely to heat up the most is the layer where the contact is being made. So this region over here, and this is also the region where the greatest amount of ionization will occur. Stellar core matter thus causes heating and increased ionization of all Earth's layers, but especially the layer where, as I said before, contact is made. And this is why stellar core dust entering the Earth's upper atmosphere gives rise to noctilucent clouds, i.e. clouds that emit light in the upper atmosphere. Thus, the presence of Planet X system objects inside the solar system leads to heating and ionization, especially in the outer layers of solar system objects, at least for as long as they have energy reserves in their cores. The Sun seems to now be running low on energy reserves in its core and is thus going dark, but its activity greatly increased between 1850 and the year 2000, which we can see here in this data. And this data comes from ice core sample data, and from it we can decipher the solar activity as a function of sunspot number. And that activity seems to have increased from about 1850 and has greatly increased until in the year 2000 it's much greater than it's ever been in the last 1,200 years, which takes us back to 800 AD. So the year 1850 is also the year that noctilucent clouds started being observed on Earth. And thus it is the year when stellar core matter started entering the atmosphere. In other words, this was the year when the Planet X effect was first observed on Earth. In conclusion, the energy transfer mechanism from Earth matter to stellar core matter causes heating and ionization of the Earth matter, which makes contact with the stellar core matter. Thus, the presence of Planet X system objects and matter, such as the debris which these objects generate, gives rise to the Planet X effect, which is the heating and ionization in any contact region, and which is likely to occur to a greater degree in the outer layers of solar system objects, which are planets or stars, and the solar system itself, that is at the boundary of the solar system and interstellar space. And these are the references. This is Dr. Claudia Albers, Planet X physicist. Thank you for watching.